You know, in modern software, we get really obsessed with the logic, right? The tiny, intricate gears inside the machine. But what if I told you the real challenge today, the biggest one, isn't what's happening inside the box? It's the connections, the wiring that links hundreds of these boxes together. Mastering that wiring, well, that's the true art of being an architect today. And that's exactly what we're going to do. We're going to drop the blueprint.
This quote just hits the nail on the head. It perfectly frames the challenge for every single one of us in the field. We've gone from being these solo coders, crafting a little masterpiece in a corner, to being system orchestrators. Our job now is to make sure this massive, sprawling fleet of services can all talk to each other reliably. The strength of the building isn't in the bricks anymore, it's in the mortar. And if that mortar cracks, the whole thing comes down. I don't care how perfect each individual brick is.
All right, so here's the game plan. We're going to start with this art of wiring, then we'll take a tour inside what I call the Monolith Fortress to see what's going on in there. Then we'll talk about escaping that fortress into the much more flexible world of microservices. After that, we'll learn the secret language of REST, figure out how to design APIs like a pro, and finally, we'll meet the newest and maybe weirdest member of the team, the AI Apprentice.
So yeah, this is our new reality. It's a total shift from being a coder to an orchestrator. Think about it. 10 years ago, your biggest headache was probably making some algorithm run a little faster. Today, your biggest headache is making sure the payment service that's written in Java can reliably talk to the inventory service written in Python, even when the network is having a bad day. If you get this wiring wrong, you're not building software. You're just building a logistical nightmare.
Okay, let's start our journey inside the monolith. This is that giant, single application fortress where literally everything lives under one roof. Now, inside these walls, the most common code smell, that first hint that something is starting to rot architecturally, is something called tight coupling. It's where all the different components are so tangled up and hardwired together that if you change one little thing, it just sets off a chain reaction of failures everywhere. It makes the whole fortress super brittle.
I mean, look at this line of code. It looks so innocent, right? This driver equals new driver. Simple. A car makes its own driver. But this is a ticking time bomb. What happens when the business rules change, and now a driver needs a license before it can even be created? Boom! Every single place in your code base that has new driver is now broken. You got to go on a scavenger hunt fixing every single one. That's not just code, it's a maintenance disaster just waiting to happen.
So how do we defuse that bomb? The solution is this really powerful pattern called inversion of control, or IOC. The easiest way to remember it is with the old Hollywood principle. Don't call us, we'll call you. See, instead of your code actively creating its own parts, like the car building its own driver, you flip that control. You hand it over to a framework. The framework is now in charge, and it provides or injects those dependencies when your code needs them. Your code just has to say, hey, I need a driver, and the framework figures out how to make one and deliver it.
This analogy makes it super clear. In the old, manual way, your code is the chef. It has to know everything, where the kitchen is, where the pans are, how to work the stove, all of it. But in the IOC model, your code is the customer. It just sits down at the table and trusts that the waiter is going to bring a perfectly cooked egg. That waiter, that's the IOC container. It's the part of the framework that handles making all the objects in your app. Your code doesn't need to know a thing about how the kitchen is wired up.
So, how does the waiter actually deliver the food? Well, this injection can happen in a few different ways. The absolute best way, the architect's choice, is constructor-based injection. This is awesome because an object gets everything it needs the second it's created, and those things can't be changed later. We call that immutability, and it makes your code way safer. Then you've got setter-based, which is kind of the fallback plan, good for things that are optional. And last, there's field-based injection. It looks easy, but architects pretty much hate it. It uses some behind-the-scenes magic that ties your code directly to the framework, which totally defeats the purpose of what we're trying to do here.
Okay, so we figured out the internal wiring of our fortress. But what happens when the fortress itself becomes the problem? When it's just too big, too stiff, too slow to adapt? We've got to shift our thinking from wiring pieces inside one application to wiring entire applications to each other. And this, my friends, leads us to the strategic rise of microservices.
And here's the fundamental trade-off. The monolith, our fortress, is often quicker to get started with, but it can easily become what I call a one-language prison. If you're built it in Java, well, everything's got to be Java from now on. And here's the real kicker. It scales as one giant block. If one tiny part of your app, say the part that processes images, gets really busy, you have to deploy and run more copies of the entire fortress just to handle it. Microservices, on the other hand, are like a fleet of small independent ships. Each ship is its own service. You can just scale up the image processing ship, and you can build different ships with different technologies. One in Java, one in Python. It's the ultimate form of loose coupling.
But, and this is a big but, all that freedom comes with a price tag, complexity. We've traded the internal complexity of the monolith for the external complexity of wiring this whole fleet together across a network that can and will fail. So how do we make sure a ship built in a German shipyard can talk perfectly to one built in a Japanese shipyard? We need a universal protocol. We need a standard handshake that everybody agrees on.
And that universal handshake is REST. It stands for Representational State Transfer. Now, REST isn't a specific technology or a library. It's an architectural style. Basically, a set of rules for how to build web services that can talk to each other. It has become the absolute standard for wiring microservices together. It's the reason a web front-end written in JavaScript can talk to a back-end in Java, which can then talk to a data service written in Python. They all agree to speak the language of REST over the network.
Now, to really speak REST fluently, you have to understand its grammar, and that's defined by the core HTTP methods you see here. First, look at the safe column. An operation is safe if it doesn't change anything on the server. A GET request, for example, just fetches data. It's safe. You can do it a million times and the server's state won't change. But the real secret, the concept that truly separates the pros from the amateurs, is that last column, idempotency.
And I really want to pause here because this is so incredibly important. Idempotency is not just some fancy word you memorize for a job interview. It is the bedrock of reliability in a world where networks are fundamentally unreliable. An operation is idempotent if doing it multiple times has the same effect as doing it just once. Think about a light switch. Flipping the switch isn't idempotent because if you do it again, the light turns off. But setting the switch to the on position, that is idempotent. You can do it 20 times in a row, the light just stays on. So the key thing to burn into your brain from that table is that get, put, and delete are designed to be idempotent, post is not. Let's see why this is a system's ultimate safety net.
Let's walk through this nightmare scenario, nice and slow. Step 1. Your app sends a put request to update item number 42. Step 2. The server gets it, everything works perfectly, the database is updated. Step 3. Disaster. The network dies before the OK message can get back to your app. So now, your app is totally in the dark. It has no idea if the update worked or not. Step 4. This is where idempotency saves the day. Because put is idempotent, the client can just retry. It safely sends the exact same request again. Step 5. The server gets it and just updates the same item again with the same data. The final result is correct, no harm, no foul. Now just imagine for a second if that was a post request to create a new item. A retry would have created a duplicate. That's a huge bug. This is why understanding idempotency isn't optional, it's everything.
So what kind of data are these services sending back and forth? Well, they're speaking JSON. It stands for JavaScript Object Notation, and it's become the universal language for REST APIs. You can see it's super lightweight, easy for humans to read, and just uses simple key-value pairs. Objects go in curly braces, lists go in square brackets, that's pretty much it. It's simple, elegant, and every programming language on Earth can understand it.
So we get the protocol, we get the data format. Now let's talk about design, about style. Because it's one thing to make an API that works, it's a completely different thing to design one that other developers actually enjoy using, one that's intuitive and predictable. This is all about creating clean, professional blueprints for our services. This slide shows the single biggest mistake I see from developers who are new to this. They put verbs in their URLs. You don't need a path like get/getBooks. The HTTP method, get, is the verb. It already tells us the action. A professional REST API uses nouns to identify resources. The path tells you what you're working with, the noun, like /books or /users, and the HTTP method tells you what you're doing to that noun. It's just cleaner, it makes more sense, and it's how it's done. And beyond that, there are a few other critical rules. First, use logical nesting. To get the reviews for a specific book, a path like /books/ID/reviews just makes sense. But be careful, don't go crazy with this. More than 2 levels deep and things start to get really confusing. Second, and this is non-negotiable, you have to version your API. Always put the major version right in the path like /v1/books. Why? Because your API is going to change.
And when you have to make a big change that breaks things, you can release /v2 without destroying every app that was using the old version. We manage this with semantic versioning, major.minor.patch, to tell people what kind of changes we're making. Okay, we've built our fortress, we've wired our fleet with REST, we've got our professional blueprints, and now a new developer joins the team. This one is crazy fast, speaks every language known to man, but it thinks in a fundamentally different way. Let's talk about the AI Apprentice. The AI researcher Andrej Karpathy had this great quote: "The hottest new programming language is English." And he's right. We're using plain English to ask AI to write our code, but we have to remember that these large language models are stochastic. That's a fancy word for probabilistic. They are making statistical guesses to predict the next line of code. They are not deterministic, like a normal computer where 2 + 2 will always equal 4. And that probabilistic nature can be a huge problem in a production pipeline that demands predictable, reliable results.
And this isn't just some theory. Look at this data from a study on GitHub Copilot. It shows that even as these amazing tools get better, they still suggest insecure or vulnerable code a shocking amount of the time. Yeah, it's improving, but think about that number for the newer versions. It means more than 1 in every 4 suggestions could have a potential security hole. Speed is awesome, but not if it comes at the cost of safety and quality.
And that brings us to one of the most fundamental truths in all of software engineering, from Robert Martin's 10x rule. The point is, if an AI helps us write bad, messy, or insecure code, but just does it faster, we haven't won anything. All we've done is created a giant pile of technical debt for the poor humans who are going to have to read, debug, and fix that code 10 times over.
And this brings it all back to our job as architects. As we start using these incredibly powerful new tools, we've got a choice to make. Are we going to use AI to build better fortresses and more resilient fleets guided by these solid principles of good wiring and professional design? Or are we just going to help create the next generation's logistical nightmare, only faster than ever before? The blueprint is in our hands.